golly, you know, putting man on the moon, the Apollo program, was an incredible, incredible achievement. And we're going to hear today from a group of an astronaut and some of the engineers that are behind that accomplishment. And they took on, and they will tell you more about it, so I will just use a couple words, at a point to gather a group of them, connected engineers, physicists, astronauts who had been involved with the Apollo program, thoroughly versed in atmospheric science, you might say, and with the task of getting man on the moon and bringing them back in complete safety. So your engineering models are very important and need to be tested and verified and validated for that kind of success to happen. And they, several years ago, asked themselves as a group with their expertise and experience to really look at the prevailing climate science and assess it. Is this credible? Is this a truth? It's declared as the dictates of science by our president that must be followed through a democratic process or not, which is not the way most scientists understand their methodology. And they have, over the last years, really thoroughly looked at the science, and they want to share it as they see it from a very important past experience and perspective. And to return to my first comments, I'm so moved by to know and to listen to these people at the heart of that accomplishment of putting man on the moon. The Texas Policy Foundation decided we would like to recognize them. And so I don't know whether you all want to stand up, or are you the official, Hal? But we have an award, modest in its size, but very, very big in its, and here's what it states. The Texas Public Policy Foundation recognizes the team at the Right Climate Stuff for defending the integrity of science and putting man on the moon. Thank you for all you've done as this team, and also for putting man on the moon.
Well, thank you. This is totally unexpected. There are a few of our research team members here that aren't on this stage. I'd like to ask them to stand and be recognized.
Please do.
And Leighton, you're part of that group.
And our first speaker will be Walter Cunningham. A very diverse background in some ways now, but I can't resist beginning with the headliner. He was selected as an astronaut in 1963, and in '68 he was the pilot of Apollo 7. And he began his career as a Marine Corps fighter pilot and holds the rank of colonel in the Marine Corps, retired with 4,500 hours of pilot time. He also has a master's degree in physics from UCLA, and is a graduate of Harvard's Advanced Management Program. He, in turn, is also now the chief executive officer of 4 companies and a founding general partner of a venture capital fund. He spent 5 years on the advisory board for the National Renewable Energy Laboratory, and is author of, and I want to get this book, I've not read it, called The All-American Boys. Is that correct?
Yep.
But thank you, Walter, for coming to speak to us today, and we're honored to have you here.
Thank you very much. And I'm sure the system's going to work, and I'll be putting the slides up there. Actually, when I agreed to come do this, I thought I was going to be dealing with both realists and alarmists. And it's obvious after being here yesterday afternoon that I'm really just preaching to the converted. I'm not a climate scientist. My associates here are really. But I have spent my life as a physicist. I've been analyzing things and assessing data, engaging in critical thinking and forming opinions for many, many years. As a fighter pilot, I began to focus on the weather over 60 years ago. And so what I'm going to do this afternoon, it'll get working, I guess. What I'm going to do this afternoon is I want to talk about some other approaches besides science to see if it will leave all the doors open for all the science I've seen in the last couple of years. And as you mentioned earlier, for more than 40 years, people have been asking me about how fragile our planet appears from space. And I always have to tell them, really, what I was most impressed about was the beauty of our planet and the fact that we have survived changes in climate for 4.5 billion years. Society has developed by this. We made it. Thank you very much. And there are very, very many complex drivers of our climate. Works. And human-related carbon dioxide is really just a tiny piece of one of those small factors that are up there. And we have long known that the sun, the oceans, variations in the Earth's orbit are the principal drivers of our changing climate. And our life has evolved by our adapting to all those changes. And we ought to also know by now that climate change is still one of the least predictable fields of science. Actually, climate science was a respected field until about 30 years ago, and that's when some of the climate scientists began to ignore scientific discipline. In the 1960s, a small group of people focused on a small temperature increase since the Industrial Revolution, and they hypothesized, that's their gifts, if you will, that the tiny amount of carbon dioxide that we humans were generating is controlling the temperature of our planet. I hesitate to call them scientists because they abandoned scientific principles with their speculation about the cause of future temperature changes. Those alarmists, they would have you believe that climate change is a threat to our civilization. The alarmists also invented something called consensus science, and they managed to sell it to many politicians, to the media, and to the public. Well, consensus is probably okay in politics or with opinions, but it's certainly not okay in science or questions that demand objective answers. As realists, we try to avoid the impact of actions that are taken based on bad science. These actions that will be devastating really to all of us. Climate alarmists would have you believe that 1, carbon dioxide levels are abnormally high. 2, higher levels of carbon dioxide will raise the Earth's temperature, and that will be bad for humans. 3, that warmer temperatures will put humans and our planets at risk. And 4, humans are capable of overriding natural forces to control the Earth's temperature. And today, instead of the alarmists presenting data to prove their new hypothesis, they are challenging skeptics like us to disprove their hypothesis. And to tell you the truth, the public really today doesn't know what to believe about humans controlling the temperature of our planet. The global warming war is really being fought on a number of fronts. There's a scientific front, the public perception front, the political front, and the media front. Data from the past 600 million years shows both temperature and carbon dioxide are near their historic minimums. And the last time that they were simultaneously at such low levels is about 300 million years ago. And about 550 million years ago, the carbon dioxide level was 12 to 15 times higher than it is today. Even in the last 10,000 years, there have been many periods when temperature was higher than it is today. To be truthful about it, today we are experiencing the longest and coolest interglacial period on record. And believe me, the next ice age is long overdue. In spite of this reality, that was the one I should have had a minute ago. In spite of this reality. Alarmists challenged the accepted theory of, I'll get it right. They challenged the accepted theory of climate change for a new, and we all know, if we're involved in science, that for a new hypothesis to be accepted as a theory in the scientific arena, that it's got to be confirmed by considerable evidence, and secondly, it has to survive all attempts to disprove it. Without satisfying either of these criteria, the alarmists have managed to fool most of the public that their hypothesis was an accepted scientific theory. They also cite a correlation between temperature and carbon dioxide levels. Well, correlation is not causation. And if it were, compare the correlation of temperature with solar activity, and then compare the correlation of temperature with carbon dioxide over the last 130 years. Pretty obvious which is the difference there. The only thing that alarmists are able to cite in support of their hypothesis is their own mathematical models, which they developed to prove that human-created carbon dioxide is a dominant factor in controlling the Earth's temperature. Well, their climate models have never successfully predicted anything. And models are based on assumptions. That's opinions. And models are not data. After years of searching, I have not found one piece of empirical evidence that man-made carbon dioxide has a significant impact on our climate. Human-created carbon dioxide, as you've been hearing for half a day at least, is 0.001% of our atmosphere. And today, that's about 400 parts per million. The alarmists are predicting that they would have world disaster if that reaches 800 parts per million. Well, I can tell you that in the Apollo 7 spacecraft, where I lived for 11 days, it was a closed environment at 100% oxygen, and of course we breathed out carbon dioxide, and we monitored the levels of it. Our carbon dioxide alarm went off at 3,000 parts per million. And today in the shuttle, well, not today, they got rid of the world's greatest airplane here not too long ago. In the space shuttle, that setting was at about 5,000 parts per million. And I've been told, but I haven't personally been able to confirm it, that on the International Space Station today, the alarm goes off at 7,000 parts per million. We should all know this, though. We've got nuclear-powered submarines that with dozens of crew members on board, and they can stay submerged for up to 4, 5, 6 months. Those subs, their alarm goes off at 8,000 parts per million. Well, I don't want you to think that all I ever pay attention to is just that kind of evidence. I do recall one piece of evidence that supports the fact that the Earth is getting warmer. I thought I'd include that one for a minute. That's just to give us a break. Well, with history, facts, and scientific discipline all on the side of realists, then why is human-caused global warming still debatable? Well, I think that the alarmists refuse to accept that today's weather is consistent with our historical climate variability. And they are loath to admit that we humans have little control over natural forces. True believers that humans are the cause of global warming cannot be reasoned out of their position, because it wasn't reason that got them there in the first place. It was emotion and politics. And while realists are winning, I believe, on the scientific front today, the alarmists appear to still be winning in the court of public opinion and in the political arena. And we let them control the semantic high ground. For example, human-caused global warming it's evolved into climate change. At this stage, the battle for public perception seems more critical than the scientific fight. The media, the public, and most politicians may not be scientific, but that does not prevent them from playing a major role in this debate. Journalists influence a great many readers, and most of them are aggressively pushing humans causing global warming. That is why I try to focus the media and the public's attention on some points that are not really scientific. Number one, the public should know that today's disagreement is not about climate change, it's about the cause of climate change. Two, you should always refer to the alarmist claim we should all refer to the alarmist claim, as human-caused global warming, not as AGW, climate change, or climate disruption. Three, the media, the politicians, and the public should not simply buy what others are telling them. They should examine the data themselves. Four, it should be made plain that what alarmists are pushing is not a theory. It is a hypothesis. That is their guess based on their interpretations of their observations. Well, alarmists have not even come close to meeting the criteria for a theory. Historical data is not just another opinion, and the public should be looking at historical data before forming their opinion. Now, I have not found one piece of evidence that supports the alarmist hypothesis. Here are my conclusions and opinions. Number one, based on historical data, there is no reason to be concerned about today's temperature or temperature trend. Number two, human-produced carbon dioxide plays a minuscule role in global temperature when it's compared to the natural factors. Three, there is no reason to believe that today's carbon dioxide and temperature levels are the ideal ones. Higher temperatures and higher carbon dioxide levels will save more lives than lower levels will. And four, it's a fantasy to think that humans can have significant influence on global temperatures. Now, if any of you are concerned about one of the greatest scientific hoaxes of all time, check the data and form your own conclusions. Don't just buy the opinions of others, and that includes me. Thank you.
We have next Dr. George Stegemeier. Did I pronounce that correctly, sir?
Right.
Also a member of the Right, I can never say it exactly right, the Right Stuff on Climate, the Right Climate Stuff.
Yes.
He is a petroleum reservoir engineer with over 50 years of experience in thermal engineering. And he's worked as a research engineer in areas to improve the oil recovery process, and later as a manager for fundamental research in this area. In 1993, he formed GLS Engineering, and from then forward provided he's applied this entity to studying the thermal engineering issues with global warming. His current book, Principles of Geosolar Engineering, is a study of the energy balance of the Earth's atmosphere with the intent of quantifying the role of CO2 in the Earth's global temperature. Thank you, Dr. Stegemeier. We welcome your remarks.
I'm another not climate scientist. I'm a petroleum engineer, and I am trying to understand how the overall energy balance of the Earth occurs. And we go back a long way to begin. The political science of global warming has created the greatest controversy in the scientific community since Galileo challenged the settled science theory with his experimental methods. Now, Galileo was not just a scientist, he was an engineer and he was a mathematician. And so that perhaps justifies me standing up here as an engineer talking about climate science. The subject of the engineering of the whole system is way too complicated to address here in the few minutes we have. And Hal wisely said, just look at the CO2 content, which is an interesting subject in itself. But first, let's talk about the overall balance. And the overall balance, oops. Here we go. As I say, it's extremely complicated. The science may be settled, but the engineering certainly is not. And what's involved here are about 20 of the laws of nature. And I'm going to just show them to you. Oops. These are all the considerations you have to have. And all these laws were established back in the 19th century. And the settled science of global warming is already settled. The engineering certainly is not. And it involves a number of disciplines. Here they are. There are so many that no one person is able to understand the whole thing. And so I'll be looking at it from a point of view of perhaps just the petroleum engineering aspect of how that affects the CO2 level in the atmosphere. So as you see, it's just one item there that we'll be talking about. If we went to the whole picture, it would take a very long time. Now, let's look at CO2 in the atmosphere. The first question is what is the average amount of CO2 in the atmosphere? We listen to the 400 parts per million, and how good an average is that? Well, I first looked at historically, and for 100 years now, the analytical chemists have been able to measure concentration, so that's done deal. The sampling location is not. Back in the first half of the 20th century, the sampling location was a critical thing. All these samples were taken on land at sea level in the northern hemisphere, where we had green plants and we had lots of burning, most of the burning of fossil fuels. The sampling frequency was variable, so we couldn't really see trends there. By the middle of the century, though, however, we started establishing observatories. And the Scripps Institute did the one at Mauna Loa that most of you see usually. But this one was it was 2 miles high. It was out in the middle of the Pacific, so that was a good point. It was on a volcanic island, which is not a good point. And let's see. Well, it was about 20 degrees north latitude, so that's okay. Fortunately, there was a second observatory established by Cicero. That's the Commonwealth Scientific and Industrial Research Organization, and the government of Australia sponsored that one. That one is way down 40 degrees south latitude in the middle of the Pacific, or halfway between the South Pacific and the Indian Ocean. The first land you see there is Australia, is South America, from one looking west and looking east to South America. So it's lots of ocean out there, and it's a very neat place to make a measurement. It fortunately is at sea level, so we have now one observatory very high and the other one low. And this is the combination. And you see here the red cycles are the Mauna Loa data, and the Southern Hemisphere Tasmania data are just a few parts per million. So this is something that, let's blow it up a little bit. I'll look at just a few cycles here. And this very nicely demonstrates the green plant effect. From May until October, the green plants are sucking up the CO2, and then the second half of the year, they again are rotting, and so they're putting energy, CO2 back in the atmosphere. Now, how are we going to predict how much more additional CO2 will result from burning of fossil fuels? And first of all, you need to look at the only thing we have a measure of, and that is the amount of production of oil, gas, and coal. And that one we know because we buy and sell this stuff. We've known since the 19th century how much of that. But we really didn't have good orderly data until about 1980, when the DOE, the EIA, began reporting yearly oil, gas, and coal production. And from that, you can't just quite look at the production, though. You also have to look at what part of that production was burned, because we don't burn it all. We make a lot of chemical products. We put down asphalt highways all over the place, and those are all either sequestered or only partly oxidized. So you have to correct for that. That's on the negative side. On the positive side, we manufacture cement, and we also burn a lot of wood. But fortunately, all those lower items, the last four at the bottom, are offsetting. So I think it's a fairly good assumption to say, let's just look at the production of oil, gas, and coal and calculate then how much additional. And that calculation is, you take a volume, say a barrel of oil, and you look at the heating value of that barrel. It's about 6 million BTUs, and you multiply times the amount of carbon compared to the amount of hydrogen that you're burning, and you get a fraction. And from that, get a total amount of energy that you got from burning carbon. From that, you can calculate the mass of the carbon. If you go and look at the amount of mass of the air, you can do that easily in a calculation of, we have 15 pounds per square inch, and you have 15, and have the surface area of the whole world. From that, you derive the parts per million of CO2. And I'll show here this calculation. And this one is an amazing thing that happened. From 1980 to 2010, it's almost a straight line correlation between the vertical scale is the Mauna Loa data that's measured. Completely independent of that, calculating is the amount of CO2 that we've generated. And notice that in addition to being a nice straight line, we've put in about 100 parts per million of CO2. What's remaining is only about 50. So it's just about half of it remains there. And the rest of it goes back in the ocean, or else it goes to the bottom of lakes, the forest floors, and all that, because all this accumulation that eventually makes petroleum or coal is that part that's not oxidized every year. And you saw in that earlier slide, there's a sucking up of the CO2 by the green plants, and then there's rotting every year. Okay, now we'll go a little bit broader. I've established a trend there with a straight line, and this one now is on a broader scale. If you look at the red dots, those are the data that you just looked at. We can now plot the same kind of thing on the vertical scale being the Mauna Loa data, the horizontal scale being the amount of combusted CO2. And if we back extrapolate, we go back to a straight line would take us back to about 300, and that would be the pre-industrial type. And it's a little bit at odds with the I-score data from, let's say, about 270. Now, we go the other way, it's the way to make the prediction. And that one is, I can, if you say I want another 100 trillion barrels of oil in the reserves, I can slide along the horizontal scale, go up to the straight line, back over to the left-hand scale, and tell how much CO2 would be remaining in the atmosphere. And so, but we have to distinguish now between the history, that's the topper one, the historical production, and what we call reserves and resources. 2 minutes. Okay, I'm going to have to speed this up quite a bit. The difference between reserves and resources have to do with an engineering aspect of if you declare reserves, you go to jail if you confuse them with resources. And there's been a lot of confusion with resources and how much more CO2 we'll eventually have. And we can get our reserves easily with using King-Hubbard's method. And if we look at oil production, we get a straight line that will extrapolate to how much reserves we have of oil, gas, coal, not. We're not on the trend yet on the King-Hubbard type decline. And let me pass that one. Now, the fossil fuel reserves are either proven or probable or possible. The proven is, you already know that amount from decline curves of particular oil fields. The probable are fields that you might produce if the oil goes up. The possible are a big scatter of things. And this could take a whole talk on the fossil fuel resources, but they involve the sedimentary basins of the world. You have the conventional oil fields. There are unexplored parts on the continents. There is a deep offshore we might find big fields, the Arctic and Antarctic. The source beds are all this new stuff that we might have from fracturing. And from fracturing, we're looking at reservoirs now that might be much larger than the conventional reservoirs of the world, but they're very tight. And I am not very optimistic about the total volume that we'll have compared to the total line. Oh, two more. The methane hydrates are in the probable, or possible, not probable. The biogenic gas is gas that might come out of the center of the earth, and that is far beyond anything like of that. So back to this one, if we look at, without a pioneer, I'm having trouble saying that, but on a horizontal scale, if you go out to the red, farthest dot, red dot, that's the total amount of production that we've had forever. If we have twice as much stuff, and that thing called mature reserves is what we're fairly well certain of. If you look at the amount of CO2 from that, you get about 500 parts per million. Now, people are a lot more optimistic about other parts of the world, so that takes us up to about 600 parts per million. And to summarize it, I'm not going to talk about CO2. Here we have it from reserves. We get up to as much as 600 parts per million. From resources, possibly 700. Okay, that's about all I have to say.
We're next going to hear from Dr. Hal, and I always mispronounce his lovely French name, Doiron. Okay, Hal Doiron. Hal organized the right climate stuff and drew together the research team of more than the 25 of the NASA Apollo program veterans. And he spent a good part of his life as a young physicist working in NASA, and one of his key areas of work was developing the Apollo lunar module, landing dynamics, simulation software. Academically, he had all the disciplines necessary for such a task as a physics degree and a mechanical engineering degree. And I would think there would be some fancy mechanical engineering in the Apollo lunar module for landings. He joined this, he organized and initiated this organization in 2012, and I think its contribution is obvious as we see here today. And so, Hal, I welcome you to hear your remarks.
Thank you, Kathleen. I took a sneak at the bio that George Stegemeier submitted for this conference, and I know what a modest man he is, but George is a member of the National Academy of Engineering. I know he has over 100 patents from his time as a petroleum engineer and thermal recovery of all. So he is a real thermal scientist. And I just want to thank George. George's older brother, Richard, is also in the National Academy of Engineering. And together they've been lobbying with the leaders of the National Academy not to jump on board with this global warming scam. And so far they've been successful. Other national academies, the National Academy of Science is all in. But maybe the engineers are the last bastion of hope to get some sanity into this process. So I really thank you, George. George has some astronaut friends, and he found out about our group forming, and he came and approached me and said, I'd like to be part of your group. And he's been a tremendous part, as well as several other research scientists from the Houston area who don't have a NASA background. But our core group are really Apollo program veterans. So I'm going to talk today about how we set out as a group of aerospace engineers primarily to understand the climate issue. I think Leighton Stewart, he threw the challenge out at a NASA meeting that he spoke at. He said, you NASA guys from the Apollo program still have some street cred. You need to take an independent look at this. And we ended up doing that. And so here's our report today on what we found out. We're a volunteer group. We're not funded. We just did this as a volunteer activity of NASA retirees. But we did have some other experienced researchers join us, and we're very happy about that. Our initial goal was determine the extent to which burning fossil fuels can cause harmful global warming. And we set out, we didn't know how to do it. We're not climate scientists. My interest in climate maybe was because I was a pilot and I had to learn about weather to make sure I didn't kill myself in my airplane. So I've studied weather, but I didn't know anything about climate. This chart has been shown before at this conference. It's from Dr. John Christie at the University of Alabama, Huntsville. In December 2013, he presented this chart to Chairman Smith's committee, a subcommittee of it. And these were the models, the results of models that the United Nations had used to put out their most recent report. They didn't show this data, but it was in the cloud, and he was able to get to it and plot it out, and then compare it to data that he had from satellites and balloons. And this goes back to 1979 when satellite data became available. And it just shows how bad these models are at predicting reality. These temperatures are from the mid-troposphere in the mid-tropics. but this is a place where climate models say is going to get the hottest. So the biggest signal of this human-caused global warming should be at this point where these temperatures are measured. And it's clearly these models are no good. Our NASA policy in the manned program was we're forbid to use unvalidated models for any kind of a decision for design of a spacecraft or for an operational decision about what to do if we had a threat. You just don't do it. So as a group, when we saw these models are not validated, we weren't distracted by them. We just took them off the table. Said, you know, we're going to have to do this a different way. We don't have the supercomputer to run these models anyway. Is there a way we can look at the data and draw some conclusions? And so we focused on the physical data. We did develop a simple model based on conservation of energy to try to help us understand the data. And I'll talk about that today. Whoa, what did I do?
In just a moment, I'll find out.
Where do I aim this thing? At you? I'm gonna have to wait. Okay. So I'm really a modeler. That's what I've done all of my career, almost 50 years. Even if I'm looking at data, I want to have a model to try to understand what all the wiggles in the data are. So we eventually got to the model we're using now. But since I know I'm not going to get through this presentation, I want to give you the bottom line conclusions from our 3.5 years of research. George has shown how much CO2 we think we can get in the atmosphere by burning all the known reserves of fossil fuels on the planet. And yeah, we might go by that, but this is a rigorous analysis showing this is what our government says are the worldwide reserves. Oil and natural gas aren't too much of the issue. Coal's the issue. Coal's the big unknown, and it's the big amount of carbon out there. But we think that due to worldwide rising energy demand, and the undeveloped world wants energy, and they're going to get the right kind, I'm sure. Fossil fuel prices in general are going to rise, and as these reserves are consumed, like any commodity, the price of energy is going to rise, and we're going to be looking for cheaper alternatives. So we think a market-driven transition to something else, which we don't know what it is, but there's going to have to be a lot of research to figure out how do we meet the energy demand of the Earth. And I'm confident we'll figure that out. But we're going to limit the amount of CO2 that ever gets in the atmosphere. So we think that we're going to have a transition away from fossil fuels, market-driven, before we ever have a climate problem. What we need, in my view, and the reason I got into the climate, we need a national energy plan to assure me how are we going to get from where we are today to where we need to be in another 100 years. I mean, we had a plan on how we were going to get to the moon and back, and it told us this is the R&D you need to do. We need to understand that your spacecraft isn't going to burn up. How do we know that we're not going to burn up coming back from the moon? A lot of research had to be done to make those engineering decisions. I don't know that the government should lead this research, but the way they're spending their money now is not, it's helter-skelter. It's not on any logical plan to get to a certain goal.
I think.
So I want to see better taxpayer money used. And we think the climate alarm is causing irrational energy-related public policy decisions. I think that's clear to everybody here. Okay, so this took us a while, but got to this simple model of an energy balance that determines what the Earth's surface temperature is, the global average. We got the sun beating down on us gives us all this energy, and some of that energy from the sun is reflected with the Earth's albedo, which is like the reflectivity. It's a fraction of, it's about 0.3. So some of that energy from the sun is reflected before it ever gets into our atmosphere, and CO2 can work on it. The other big part is radiated back to space, and it's at the upper right. That's a well-known law, Stefan Boltzmann law, and it says some constant emissivity times the universal constant sigma times temperature to the fourth power, and that's about 238.5 watts per meter squared. And a little bit of that surface heat goes down into the oceans, and that's probably variable. So we can write an equation that talks about the energy leaving due to radiation from the Earth's surface and the energy coming in, and changes in the reflectivity, changes in solar, and changes in the amount of heat going in the ocean. And so we apply a little calculus to that, a basic equation, which we have a lot of comforts in, and I'm not going to go through it, but basically, in the theory of human-caused global warming, the emissivity, the effective emissivity of the Earth's surface is a function of carbon dioxide, water vapor, other greenhouse gases. I want to go back and make one point. Notice the little dash line above. That solid line is an arc of about 1,000 miles of the Earth's surface. And the dash line represents the part of the atmosphere that actually affects the emissivity of the Earth. And it's about 14 miles up. It's at the top of the stratosphere. And after that, the atmosphere is so rare that the CO2 molecules can get out unimpeded. So this is why we idealize the problem this way. The change in emissivity due to an increase in carbon dioxide in the atmosphere is given by the top equation, and this is not controversial. All climate scientists generally agree with this equation. And then we defined a metric that could be verified we call transient climate sensitivity. Most climate scientists use a metric called transient climate response, which is how much warming we'll get on the Earth's surface if we double it at a rate of 1% per year increase. Well, you never can check that. So we said we want transient climate sensitivity to be how much warming we get from doubling CO2 in the atmosphere, the way it actually happens that we can measure, a variable rate, very slow. And so we were able to write an expression for that from the calculus we did on the equations. And it includes any kind of feedback that you think in the climate is due to initial warming from CO2. We got into some equations that modeled the human effect and the natural effects. This is how CO2 went up in the atmosphere. Our projection headed towards Georgia's 600 parts per million, which looks like it'll be somewhere in around 2130. And we can use that projection to predict how much warming we're going to get from CO2 in the atmosphere. And it's not scary. This is what was happening before the industrial age naturally. And if that's going on, we can look at that too. This is the actual temperature data, global average surface temperature data. It's not going up monotonically. There's some wiggles in it. And we modeled these wiggles with cycles. And we say, okay, based on the historical data, our understanding of transient climate sensitivity, we're going to get at most 1 degree warming by the end of this century. We can look at other cases. What if this natural climate cycle of 1,000 years, well, you're only going to get 0.8 of a degree. And we had a way to look at the worst case, and our value for transient climate sensitivity is about 1.2 C, which is falling into what most of the recent determinations of this constant from observational data are. Dr. Lindzen probably has the lowest estimate of this number, but the people that look at data are coming up with small amounts of climate sensitivity to CO2. So I'm going to stop it there. That's the way we approached it. We're very confident of these numbers because this is what the data says. And I don't care what any model says. If it can't agree with this data, then, you know, it's of no interest to me. Thank you.
Thank you. I think we have some time for questions. If you would, please.
Yes, when you look at the somewhat lower number of 600 to 700 parts per million, projecting out what the change will be, do you know what the historical record shows as far as during man's lifetime, what the upper end of the temperature would be and the effect that it had in the past of being a degree or less?
Well, the entire increase that you could associate with human CO2 is less than 0.8 of a degree since the start of the industrial age.
Yes, but is it going to matter? That's the bottom line.
Well, that's the part I'm not an expert on. I don't think it's going to matter. My gosh, the temperature in Houston varies 11 degrees centigrade from day to night. And I can't imagine that a 1 degree increase in that average is going to amount to anything.
Because I think that's the point of all the work. Is it going to matter?
No.
And to my eyes, so far, it doesn't see that it's going to matter. But if somebody comes up and says, "A degree, we're going to die," well, I still know. What do I tell them?
It hasn't been that long ago that you had ice totally covering the United States down even to the northern part of Texas. And it didn't kill people off, incidentally. But you adjust to things like this. What we ought to be focusing on a whole lot more is the adaptability of what's happening regardless. As far as I'm concerned, a slight increase in carbon dioxide is going to be better for life. It's going to be better for a lot of things.
I just wanted to make that point. There were many speakers yesterday, and there's quite a bit of research, data, concluding research that shows the increased, plant productivity and all the rest of the things. And there also are lots of studies. Someone that has taken this on well, I think, is Bjorn Lomborg, author of Kulit, that demonstrating with data that I can't remember, it was 1 to 3 degrees centigrade increase, that you get fewer you have higher cool deaths than warming deaths as far as the world in temperatures and all kinds of productivity and effort. It's a benefit to be a little warmer as far as his data.
Another way of looking at it is what is the ideal temperature of the Earth? Was 1790 the optimum for all time? Right now, the average temperature of the Earth, if you add up from pole to equator, is about 59 degrees Fahrenheit. Now, you all know that you don't keep your house at 59 degrees or you don't take a bath in 59-degree water, so perhaps a little warmer would be better.
One point, I've looked at that. One thing that we learned how to do at NASA was assess threats, especially life-threatening threats. And another part of my talk, when I have more time, is the processes, the disciplined thought process we had for assessing threats and figuring out what to do about it. And certainly we learned you don't go take action if you don't understand the problem, because you don't want to make it worse. But I looked at the warming. If we get 1 degree, let's just say we get 2 degrees all over the Earth average. This is what everybody says, and trying to get established officially as the disaster limit, which I don't buy. But this is what the common narrative is among alarmist climate scientists. based on just the physics of how CO2 could warm the atmosphere, you're going to get more warming in the poles than you are at the equator. The places where it's hot already, they're radiating it a lot faster than the Earth is at the poles. So the hot places aren't going to get hotter. It's the cold places that are going to get a little warmer. So the threat is you're going to melt a lot of permanent ice sheets and get sea level rise. And you hear a lot about that. But if you monitor sea level rise, it's not changing. Or if it is, you can't detect it, it's so small. So I would focus, if I really were concerned, about, well, what's the chance we're going to melt these big ice sheets on Greenland and much bigger ice sheets on Antarctica? Antarctica's been building ice for 34 million years. And once in a while it loses a little bit, the sea levels respond a little bit. So I would say, based on my looking at the threat, sea level rise is a legitimate concern, but it's not going to be right away. And if I were in a low-lying area like Galveston, which does have a rather high sea level rise rate because I think the land is sinking, would you try to get an international agreement with China to stop putting CO2 in the atmosphere? Or would you start building a seawall? What do you think is going to be the best investment of your money? What we're doing is absolutely stupid. We're used to rational decisions as government employees. We are not getting rational decisions out of the EPA, and they need to be investigated.
Yes, please.
Thanks for that answer. It leads pretty well into the question I was going to ask. What happens when you take this presentation, which I think was very good, to audiences, whether it's government officials or legislators or audiences with climate alarmists? How do they react to this?
Well, I would like to take this to a Congress. I'm working my way towards that goal. I think we understand this problem well enough to go talk about it. I have shown this approach since about April. I've been warned by others that Dr. Lindzen would not necessarily agree with. I would love to discuss it with him. But this is an engineering approach to figuring out what the temperature of the Earth is and what affects it. It's the exact same approach we use on spacecraft to figure out how hot's it going to get in the spacecraft and can we put a human in it. So I'm very confident with the general approach that we took. I've been giving this lecture to engineering classes, and it's well received. The young people really, at least the engineers, are well trained to be able to understand this, and I'm getting great responses. I haven't tried it out north of the Mason-Dixon line, but you know, I really think youth are looking for somebody that can tell them a rational way to think themselves through this issue.
Let me add a thought to that, because as you can tell by my presentation, I'm not busy trying to present the science and be involved in the science to do this. I'm really looking at how do we address the problem, not us, because I can tell we're true believers in what's right. It's how do you address the problem with those people who do not. And I made a couple of notes here in case somebody had asked about how many here are familiar with the expression that 97% of the scientists believe that the Earth is, global warming is going to be dangerous for us. How many here know where that 97% figure came from?
We talked about it here in the science session.
What?
We're up to speed because they talked about that last night.
Oh, where the 97% figure came from?
Yeah.
Please say it again.
Well, I have to tell you, this came from I assume it was a doctoral thesis that was back in 2009, and I could give you the names of the people. There was a lady that did this, but they solicited some responses to it. They had a five-question questionnaire, and they sent that out to 10,257 Earth scientists at universities and government research agencies. Now, they excluded solar scientists, space scientists, cosmologists, physicists, meteorologists, and astronomers from their survey. But they did include the 10,257 scientists in disciplines like geology, oceanography, paleontology, geochemistry, because they were deemed more worthy to give their opinion. Of those 10,257 people they sent out, they got 3,146 responses. That was 31% of them. And then they went and took a look at 5% of those who had identified themselves as climate scientists. So I think they sent another questionnaire out with 2 questions. But of that, 79 responded. So what you're down to is 79 out of the 10,257, and of those 79, 77 said they believed that human activity was a contributing factor in changing the mean global temperatures. Okay, 77 divided by 79, that's 97%. 77 divided by 10,257, I haven't done that, but all I'm saying is we're being fed that kind of ridiculous data. And many, many politicians today, you hear them cite that when somebody asks a question to kind of put them on the defensive about it. That's what they said. Well, what am I supposed to say when 97% of the scientists agree? It is nonsensical. It's one of the greatest scientific hoaxes in history.
Do we have time for, no, we have to start? Oh, Jim.
Yes. Dr. Doiron, I'm Jim Henry, I'm a petroleum engineer, and I studied the King Hubbard curve a lot. He was a great man, but he pointed out that the reserves of oil peaked about 1973 and are finite and are declining right now. Well, he was correct but the problem he didn't grasp is the advance in technology. Technology will change everything, and it has in this case. In about 2000, George Mitchell discovered the new frac technique, and this new frac technique has changed everything, including King Hubbard's curve. And Mark Mills has written a good book called The Bottomless Well that predicted this change. He said there's not going to be an end to oil and gas reserves, and he was right. With the new technique, we've almost doubled the reserves for oil. We've got enough reserves to last for the next 200 years. So we're not running out. This running out of oil has been used as an excuse to subsidize solar and wind. It's not a good thing. They're competing with us. Oil is down at the lowest price it's been in 15 years. It's down to about $40 per barrel right now, and it is cheap and it's affordable, and it will be lasting for the next at least 200 years. So we've got a lot, and we don't need to be subsidizing wind and energy or having a plan that we need to go to something else because we got enough. We're also, the United States is a Saudi Arabia of coal. We've got a tremendous amount of coal, and we need to use both of those to go forward into the future because it's so much cheaper. And the moral part of this is that if you use solar and wind, you cause the price of electricity to go way up, and the poor cannot afford that. So I don't want to give the impression as we go on, as you testify before Congress or anything, that we're running out of oil. That's not the case. We have enough to last for 200 years, which is essentially.
You're talking about 200 years at the current rate of
At
use?
the current rate.
Yeah, I'm
well,
afraid
no,
the current rate isn't going to stay.
No, I'm sorry, not the current rate. Whatever the rate increases, we will increase it. And it's not getting so, if it was getting scarce, the price would be a lot less.
And it's also not mentioning, that's not mentioning the kind of improvements that can come in the whole production activity over the next 200 years.
Yeah, see, don't ever bet against technology. We'll find other ways. Gas hydrides was another way.
Okay, let me comment on that. I was a friend of King Hubbard's.
Pardon me,
Oh.
and I don't want to, this panel has gone far beyond, so it's delaying the others.
Okay.
So,
Okay.
and I hope conversations can continue in the lobby and all of those, but we have,
Thank you.
we have overstepped our time.
Thank you.
Thank you all very much.
Thank you.